Hello students, in this video we will discuss the normal distribution approximation of a binomial distribution. The example that we will use is as follows. A test consists of 100 multiple choice questions. Each question has 4 choices, A, B, C, and D. What is the probability of passing this test, getting 50% or more on this test? Now the wording in this question is such that it's set up to be a binomial. We know what, let's just work on this half over here. Actually, let's just do it like this. We know that from the question, the test has 100 questions. The probability of getting any one question right is 1 out of 4, or 0.25. And what the question is asking us, go back to it, is what's the probability of passing this test, getting 50% or more? Now in a typical binomial, it's going to ask us for the probability of getting 25 or 30 or 40 correct answers. When it has something like this, this means that there is a series of repetitive questions or calculations that we have to do to solve this question. So we know that it's asking for the probability of x being greater than or equal to 50. So this would be the same as calculating the probability when x equals 50 plus the probability when x equals 51 all the way up to calculating the probability when x equals 100. So there would be 51 calculations that we would have to do to solve this question. Doing this on pen and paper would be very difficult and time consuming. What we can do is use the normal distribution to approximate this binomial probability. In a binomial probability, we have the values, or we're given n and p, and we solve for x. In normal distribution, we can draw out the normal distribution. We need to know the mean and the standard deviation. Those values aren't part of the question, but we can convert binomial distribution to normal distribution by solving for these values. We know that the average or expected value of a binomial is n times p, so this would be 100 times 0.25, or the average, the expected value of this binomial is 25. The standard deviation of a binomial is the square root of n times p times 1 minus p. So we know that n is 100, p is 0.25, 1 minus p will be 0.75. So we multiply those three values, take the square root, you should get a value of 4.33. Those are the precise values we need down here. So that's step 1 in converting a binomial distribution to a normal distribution. Now there are some kind of checkpoints we have to do in order to make sure that we can actually convert this binomial to a normal distribution. A couple of them, let's do this in purple here. A couple of them indicate that n times p has to be greater than 5, and n times 1 minus p also has to be greater than or equal to 5. So those are two kind of calculations we need to do in order to make sure that our data is large enough to be able to convert it and have a probability that is relatively close. So if we calculate n times p, we know that that equals 25, which is greater than 5, and for the second condition, n times 1 minus p would also be greater than 5, n being 100, 1 minus p being 0.75. So the two conditions are met, so that gives us kind of the freedom to know that our value, our final answer, is going to be relatively close to the answer we would get if we were to do this calculation straightly through a binomial. So I'm going to take a moment to erase this page so then we can move on. So now we know that it has a normal distribution of, sorry, why am I saying 100? Has a normal distribution of 25, and it has a standard deviation, I'm just going to list it up there again, of 4.33. We want to know the probability that someone passes this test. So to pass this test you have to get 50 or more. We're going to put 50 right there. We're going to shade in that area because that would indicate every value greater than 50. So after this becomes a three-step process. Calculate Z, find the area, make the adjustment. However, there is one little adjustment we have to do anytime when we are converting a binomial distribution to a normal distribution. Anytime when we are converting a discrete variable to a continuous variable. Binomials use the discrete variable because in a binomial we were always answering or calculating a probability that x equals a certain value. In a normal distribution we are calculating a probability that x is greater than any value. It could be a whole number, 5 or 6, or it could be values in between, 5.5, 5.6, and so forth. So we have this correction factor. So I'm going to show you how to use this correction factor. Showing it a lot easier than explaining it. What we do to apply this correction factor is this area that we have shaded in, so this area right in here that we have shaded in blue, we have to increase the size of that area. And depending on what side of the distribution you're on, it's going to make a little difference. So we're just going to add a little bit of area to that shaded in blue area. So once again, we're always adding area. The next step, let's do this in purple, is finding now the area has been increased. We know that 50 would mark the point at which that blue section begins. Now we need a value, a kind of a new x value that indicates the blue shaded in area plus that correction factor area. So that little bit extra we've added into that area has actually decreased that value from 50. It's always going to work out that we subtract 0.5 from that original x value. So our new x value is 49.5. Adding or subtracting this x value here depends on what side of the distribution you're on and depends on the question, if it's more than or less than. Best way to determine how to apply that correction factor is draw it out, shade in the original area, which we have in blue, apply that correction factor element to the shaded in area. So we're increasing that volume or area of that section, and now we can tell that we've added in more area. Our x value is going to be somewhere between 25 and 50, so we know it's going to be less than 50, so that's why we are subtracting that correction factor value from 50. the correction factor value is always 0.5, but sometimes, as I've said, we subtract it from that original x, sometimes we add it to that original x. So now that we have the new x value right there, that's the x value we're going to put into our z formula. So our z formula is still the same, x minus the average divided by the standard deviation. So we have 49.5, that new x value, minus 25 divided by our standard deviation. We get a z value of 5.67. So when you go to your chart to find that area that corresponds to that z value of 5.67, you know that our values only go up to 3.09. General rule of thumb is if the x value is off the chart, use an area of 0.5. You can tell that this last few rows, these areas are always are 0.49 and more. So basically any value greater than that, we're just going to play it safe and use a area of 0.5. So we know that the area is 0.5. Remember that this area here corresponds to this in here, 0.5. Now, just for good practice, remembering that this z, the normal distribution process, is 3 steps. Step 1, calculate z. Step 2, find that area. Step 3, make that adjustment. Our adjustment is going to be, in this case, 0.5 minus 0.5, which gives us 0. If we were to do this in Excel, we'd actually find that the probability is not exactly equal to 0, but in this case it's really small and works out to be about, let me put this in yellow here, the probability of passing this test is 1 in 130 million. So in class, I believe I had 30 or 40 students try this test, this multiple choice test with no questions and just kind of guessing what the answers are, A through D for 100 questions. And you know, the probability of passing is 1 in 130 million, or basically 0. So a couple things to understand in here is once we convert that binomial to normal distribution, it becomes a 3-step process. The only difference is we have to apply this correction factor to that new x to get to the original x to get the new x value.